The thing that's being acted on now with 2 qubits is a 4-dimensional vector. Now don't worry about that. Don't think we're going to do anything really weird or sci-fi. All we're doing is having a vector whose column has 4 elements in it. And because the gate is really an operator, it operates on the vector. How many 2-input gates are there in the other world, the classical computer world? Well, there's NAND gates, AND gates, OR gates, exclusive OR gates, and that's pretty much it. Let's begin with one that's related to the NOT gate, or the inverter bit flip gate, and talk about a controlled NOT. In other words, one of the bits is just a control bit, and the other bit determines whether the bit is flipped or whether it's left alone. So let's begin. Here's the C0 gate. Ooh, wow. It's a 4x4 matrix. We just got through dealing with 2x2 matrices. What I want to point out is, do you remember the identity gate? Look at these 4 elements here. Those 4 elements are the identity gate. And what is this? What are these 4 elements? Those are the bit flip gate. In some cases, the identity applies. In other cases, the bit flip applies. A 0, 0, which is a 4-dimensional vector, which is 1 at the top, like the 0 was before, only it's got 3 zeros below it. 1 at the top and 3 zeros below it. That's the vector that this represents. And you can see that if we have these 2 in there, all that we get is a 0, 0 out, which is the identity gate for these first 2 conditions. A 0, 1 gives you a 0, 1. That's the second row here of this gate. Now we do the bit flip for the other 2 cases. 1, 0 gives us 1, 1. 1, 1 gives us 1, 0. So this, what was a 0 in this second placeholder becomes a 1. What was a 1 in the second placeholder becomes a 0. So you can think of this as inverting, this being the data, I guess, if you will, on this second bit, and the first bit controlling whether it's a bit flip or not. Let's move on to this one. This is a controlled Z gate. Well, where's the Z gate? There's the Z gate right here, and it's only controlled by the same situation, a 0 or a 1. Now let's see if the phase is changed. Notice the minus sign here? That's the phase being flipped 180 degrees. If it's a 1, then things take over. If it's a 0, then nothing happens. So look at these 4 elements here. These 4 elements become a phase change. What's this E and this I theta? What's that all about? Well, let's consider different thetas. If the theta here is pi over 2, then that means that it's just I. Now, how do I figure that? Pi over 2, or e to the I theta, means cosine of theta plus I sine of theta. So pi over 2 would equal that value. Here's the swap gate. Notice the 0, 1 gets swapped for 1, 0, the 1 0 gets swapped for 0 1. Now how come 0 0 and 1 1 don't change? Well, if you swap those bits, you're right back to the beginning. Now let's look at the 4x4 matrix and see what's going on. If all of these were 1s, then the gate wouldn't change anything. But look at it. Everything, these are 1s and these are 1s because these two cases don't change. And in here, these 4 elements become a swap gate. The I swap, this is no big deal. It's just one of the standard cases. Notice that when we start with a 0 1, we get an I here and it swaps it. 1 0 and we get an I here and it swaps it.